Hi, this is Mrs. Baston, and today we're going to talk about quantized energy in photons, which is section 6.2. So in the last section we talked about the wave nature of light, but there are a couple things that can't be explained by that model. So one of these things is something called blackbody radiation. So when something gets hot, it glows different, and it even glows different colors depending on how hot it is. Max Planck explained this by saying that energy comes in packets called quanta. So a quantum is the smallest amount of energy that can be emitted or absorbed as electromagnetic radiation. So one example they use for this is this picture that you see here, where on the left you have someone walking up steps in a quantized matter. So that quanta would be from one step to the next. So you can only put your feet on the steps. Whereas next to it, you have, this would be something that would be in a continuous manner. So that person can walk anywhere along that ramp. Another explanation is comparing playing notes on a piano to playing notes on a violin string. If you're playing notes on a piano, you can only play certain notes. You can't play the sounds in between two notes on a piano. Whereas if you have a violin string, you could play a note anywhere along that entire string. Einstein then built on this assumption to also use it to explain something else called the photoelectric effect. The photoelectric effect is something that's seen when light is shined onto a metal surface and the metal surface ejects electrons. So this was something else could not be explained with that wave model. So he came up with the idea that energy is also proportional to frequency. So the formula that he gave us is E equals h nu. So E stands for energy. Nu still stands for frequency, but in this case, h is Planck's constant. So Planck's constant is this number here, 6.626 times 10 to the negative 34 joule seconds. So in the next slide, we're going to look at how we can apply this. Okay, so we can then use that relationship to do some calculations here and calculate energy if we're given the frequency or the wavelength. So this one says calculate the smallest increment of energy that an object can absorb from yellow light whose wavelength is 589 nanometers. So this one wants us to find energy, but we're given wavelength. Okay, now the formula we just looked at was E equals h nu. So we have h is a constant, that we saw on the previous page, so 6.626 times 10 to the negative 34 joule seconds. But in this case, we don't have frequency. Now, if you remember from the previous notes, we saw that C equals lambda nu. So if we have, and C is a constant, so if we have the wavelength, we could solve for frequency. Once we have frequency, then we could solve for energy. Now, something else you can do here is you can actually combine these two together. So I would write this in your notes next to where the other equation is. So when you combine these together, you get E equals hc over lambda. So this way you have a way to solve for energy if you're given wavelength, or you have a way to solve for energy if you're given frequency. So since we're looking for energy and we're given wavelength, we're actually going to use this equation for this problem. So I'm going to put this over here. So E equals h is a constant, 6.626 times 10 to the negative 34 joule seconds. C, this is going to, here I'm going to erase this so we can see a little better here. Okay, times 3 times 10 to the 8th meters per second. And I'm going to divide that by wavelength. Now my wavelength, because of this here, has to be back in meters. So you have to convert that nanometers to meters. So when you do that, you end up with 5.89 times 10 to the negative 7 meters. And when you solve that, you find out your energy is 3.37 times 10 to the negative 19 joules. It ends up being joules because seconds cancels over here, meters cancels, and then I'm left with joules. So joules is our unit for energy, which that carries over from what we've just been talking about in the past unit that we did. Okay, so here's another example. This one says we have a laser that emits light with a frequency of 4.69 times 10 to the 14 hertz. And we want to know what the energy is. And just like before, we still know what H is. H is a constant, 6.626 times 10 to the negative 34 joule seconds. So E equals H nu. So this one we can just use this equation because we're given frequency. Plug in 6.626 times 10 to the negative 34 joule seconds times 4.69 times 10 to the 14 hertz. And this gives me 3.11 times 10 to the negative 19 joules. Okay, now I end up with joules because remember from last time, seconds cancels out hertz because hertz is the same as 1 over seconds. So this tells me and this says for one quantum or one light packet of that particular laser. So one quantum has that many joules. So this many joules per quantum. You wouldn't have to say this, but that would be another way you could label it. Okay, then we can continue on with that, and this is the same laser. So if this laser emits 1.3 times 10 to the negative second joules of energy during a pulse, how many quanta of energy are emitted during the pulse? So we just figured out how much energy was released per quantum. So now we can see how many quanta are released per pulse doing a conversion here. So this is how much energy we have. So it's 1.3 times 10 to the negative second joules of energy are released. Now from that previous problem, we saw that there were 3.11 times 10 to the negative 19th joules per one quantum. So if we do this conversion, this tells us that there's 4.2 times 10 to the 16th quanta released per pulse. And again, a quanta is like a set amount.